Thank you, Elizabeth. And thank you for the invitation to this nice conference. And as other people, I would prefer to be in Bonn, but okay, that's life. So I will be speaking about this Mahler conjecture for even log-concave functions dimension 2. But in fact, I will be speaking about more general Mahler conjecture for sets also. And so this talk is based on results with Meyer, Barth, Hubbard, Roldan Pensado, Zvavich, and Elie Nakhle, who is a PhD student with me now. So let me start with basic stuff that you know and we have seen previously in the conference, but I will go quickly through it. So polarity and Mahler for convex sets. So we will always consider symmetric convex bodies here in my talk in Rn. And the polar set is a set of y such that x scalar y is smaller than 1 for all x in k. And for all x in k, there is a y such that x in y in the for all x in the boundary of k, there is a y which we say it's norms k, and the y is in the boundary of k polar and satisfy x scalar y equals 1. And in fact, we will assume here that our body is strictly convex and differentiable, so that this gives an exact bijection between point of the boundary of k and the boundary of k polar. And this is what I wrote here. So there is a bijection which sends to each point in the boundary of k a point in the boundary of k polar which norms it, and reciprocally, in fact, if you assume, for example, that k is strictly convex and smooth, differentiable, boundary differentiable. Okay, and now we get this map, and for example, what does it do? So as we know, all of us know, the polar of a section is the projection of the polar. And when you look at this map, what does it mean? It means really that when you look at the section, so point in the section, hyperplane section of K, so K intersected I orthogonal, where the point in the boundary of the section, they come from exactly the boundary of the point which projects onto the projection. So the point in the K polar which project, these are exactly the points which norm this X. And so you see that when you look at, because we will consider regions in K, and the corresponding region in K polar will be given by this map. And so you will see that, for example, when we will be looking and anticipating the following, when we will be looking at sections of K with positive octant, for example, R plus to the n, then the corresponding thing for K polar will be not section by a cone, or not by a convex cone at least, but by something with a non-convex boundary, okay? But whose projections are convex, which is a funny thing, okay? And now the volume product of K is the volume product of volume of K and K polar, because K is symmetric now, I recall. And it is an affine variant, so it doesn't change when you apply a linear bijective transform. And Dashko and Santalo proved that this volume product is maximized by ellipsoids, and if and only if, in fact. And something called as Mahler conjectures is that minimizers among symmetric bodies are something called Hanner polytopes, which are L1 or L infinity sum of segments, let's say, and for them the volume product is 4 to the n divided by factorial n, and one example of this is the cube. And the lower bound among all convex bodies is assumed to be, we think it is the simplicist, let's say. Okay, so there are many partial results about these Mahler conjectures, and I will just mention a few because, yeah, I want to focus also on the functional form, as I said. So Mahler proved it in dimension 2, and then Saint-Rémond, much later, of course, proved it for unconditional convex bodies. So unconditional convex bodies are bodies which are symmetric with respect to the coordinate hyperplane. And with Meyer gave 5 years later a simple proof, and this will be our starting point. And I will give it to you because it's so simple I can give it now. So we start with, so what do we want? Because of the symmetries, because it is unconditional, everything reduced to the symmetric parts. All the body can be recovered by symmetries from the symmetric parts. And so we will denote K plus is the positive part of K, and K polar plus the positive part of K polar. And we prove by induction, we will prove that volume of K plus volume of K polar plus is larger than 1 over factorial n. Okay? And how does it work? When we have done this, this is finished because volume of K is 2 to the n times volume of K plus, volume of K polar is 2 to the n times volume of K polar plus, and so this is 4 to the n times 1 over factorial n, and this was our conjecture. Very good. So how do we prove this? We just observe, this is this drawing, that K plus contain the union for I equals 1 to n of the convex hull of each section with a hyperplane of coordinates and x for every x in K plus. So this is this drawing. So this is, you take a x in K plus, you build the cone with K plus, here is K plus intersected with E2 perp, because, okay, exchange. And here is K plus intersects with E1 perp, and you draw the cone. So you have these two cones. And so this is, you have this inclusion, so you can take volume. And this inclusion is in fact essentially a partition, so they just coincide on a null measure parts. And so you get that volume of K plus is larger than the sum of this volume. And these are cones, as I said, truncated cones. So the volume is 1 over n times base times height. And the height is just xi. So this is just K plus times xi. Okay. And now you can see this is true for every x in K plus. And here, in fact, you can say that this is a kind of scalar product. This is x scalar Vk, I will call it Vk, where Vk is the sum of these things EI. Okay? If I do this, I just get this. And because this is true for every x in K plus, in fact, you can prove, you get that 1 over n Vk divided by volume of K plus belongs to K polar. Because in fact, with the correspondence I've made before, the phi, if you have an unconditional convex body, the K plus part corresponds exactly to the K polar plus part. The points which normalize points in the boundary of K plus are points in the boundary of K polar plus when you are in conditional, when you have the symmetries. So knowing that this is true for any x in K plus implies immediately that this is in the polar, and in fact it is in K polar plus. Similarly, you can do the same for K polar plus, and you get, with the same definition of V K polar, that V K polar divided by volume of K polar plus belongs to K. And now you have these two vectors, one in K polar, and this becomes to K plus also. One in K polar plus and one in K plus. And so if you do the scalar product, it will be smaller than 1. By duality, the definition of the polar that I recalled before. And so I do this scalar product, and I get that it's smaller than 1. And I can reorganize this. When I do the scalar product, I will get that directly. I write this a bit quicker, that this is larger than 1 over n squared, Vk scalar Vk polar. And I can write what it is, sum on I of, this was this definition, so K plus intersect EI perp, K polar plus intersect EI perp. The plus and the polar I exchange, but okay, I will change it. Okay, I can erase this also. So K polar plus intersect EI perp. Very good. And now this, because of the unconditionality, in fact, the section is also equal to the projection. So this is, in fact, the projection of K-polar. Because of the symmetries, when you project, usually the section is included in the projection, yes. And here there is equality. And now, because of this, we've seen before that the projection of the polar is the polar of the section. So this is K plus intersect EI per polar. And here you get volume of something times volume of something else from its polar in dimension n-1. So as I said, we are thinking by induction. So this is larger than 1 over n-1 factorial. And so you get n times here, because you have n times factorial n-1. And so this is factorial n. So this proves Mahler for unconditional convex bodies. Okay, so with Barthes, we use this method to prove for bodies having other set of symmetries. And more recently, so published last year, Elie and Shibata managed to prove Mahler for in dimension 3 in the symmetric case. So this is very good. And with Hubbard, Meyer, Roldan, Pensado, and Vavich, we managed also to simplify a bit their proof. And so the proof used two key arguments: an equipartition results and generalization of Meyer's proof. So let me explain generalization of Meyer's proof. So you have so you want to do the same, but you don't have this section equal projection. You don't have these things, so you will do a bit differently. So first you start with the definition. So you have an oriented surface. So surface, you know the normal. And you define V of S, which is the integral on the surface of the normal. So this is a vector. And C of S, it will be like the cone generated by this surface, the truncated cone. Okay. And in fact, you will apply it to S included in the boundary of K. Okay, or the boundary of K polar. And so the normal to S is the normal to K. Very good. And you consider the orientations, it is the exterior normal. Okay. And now the volume of C of S, this cone, is just 1 over n. So it's obvious. I mean, it's just computations. You can do it for polytopes. So it's 1 over n integral on S of x scalar nk of x dx. Okay, the nk is a normal. And now there is a lemma which corresponds to Meyer's lemma, if you want, is that for every x in k now, the volume of C of S, maybe I will keep this like this so you can see the definition of V. V is just the integral of the normal. So the volume of C of S is larger than 1 over n x scalar V of S. And since this is true for every x in K, you get again that V of S divided by n volume of C of S is in K polar. So this is the same statement here twice. And how you prove it? This is one line proof. So in this talk, I will give you 3 proof or 4 proof of further generalization of Meyer's ideas. So here's this one. So this one is really one line. So volume of C of S is, I recall, 1 over n, but here I will not use x, I will use z. Z scalar nk of z dz. Very good. And when you analyze what is it, if you have, so here is z, let's say, and this is nk of z, and this is k, of course. And now you take x in k anywhere, and so 0 is somewhere because it's symmetric. X, so this scalar nk of z is just the distance between the origin and this hyperplane, this scalar nk of z. And so it's larger than x scalar nk of z for every x in k. So it's larger than x scalar nk of z, dz. And now you can take out x of this integral, and you get x scalar V of S divided by n. So this is the statement. So you see it's really, and this is true for every x in k, as I said. Very good. So it's not difficult, as I said. And this proves this. And now, knowing this, Knowing that V of S divided by n volume of C of S is in K-polar, you can do the same. So this was true for any S here. I have written here S in the boundary of K. So now you take S in the boundary of K, T in the boundary of K-polar, surface, hypersurface, and you, because you have the same, you have a point in K-polar, a point in K, you take the scalar product, and you get that it is smaller than 1. And what does it give to you is that this volume is larger than this scalar product. This product of volume is larger than this scalar product. And notice that if you apply it for S equal boundary of K intersected with R plus to the n, you recover exactly Mayer's ideas. So V of S, because of Stokes' formula, V of S was the integral on the boundary of S of nk of x, and now S is the boundary of K intersected with R plus to the n, the positive part of the boundary of K. So here I've drawn something like this. So you have the boundary of K intersected with R plus 2n. And Stokes' formula tells you that when you integrate the normal of something on some surface which is closed, you get 0. So here you apply it to the something which is closed will be the interior of K intersected. It will be K intersected with R plus to the n. So there is one boundary which is this one, and you have the other boundary which are the sections. Okay. And so because the integral of the normal of this is 0 inside, the integral on this boundary is equal to minus the sum of the integral on the sections. Okay. And now the normals on each section is just constant, is minus EI. So there is this minus, so you get EI, and the volume goes out, and so you get the VK that I had before, but I wrote it with the capital V. I changed notations. Okay, very good. So this is capital VK, and here you exactly get Mayer's formula, but a bit more generalized because you have not assumed at all some unconditional property. Okay, and so the method then, so you have some lower bound of some volumes of a part of the volume of K and a part of the volume of K polar. And now the whole thing is to see how it goes when you, so applying equipartition, you can manage to cut K into pieces, and the corresponding pieces you will apply it for K polar will be exactly the phi of these pieces, the normalizing parts. And using equipartition, you can compute this product. You have many sums, and everything cancels out, and you reduce to dimension less, 1 dimension less. And so equipartition works in dimension 3, and you know it in dimension 2, so you get the result in dimension 3. Very good. So as I said, I have mentioned very small, I want to go to functional forms, and I have mentioned only a very few parts of the results known about Mahler conjecture. I wanted just to quote that, to say that Karasev proved a very, very nice particular case. So Mahler conjecture holds for hyperplane sections and projections of LP balls, BPN, and Hanor polytopes. So this is using symplectic geometry, and this is a very nice result. It was not known at all before. This is nice. So now I want to switch to functional forms. So functional forms, I recall Legendre transform. So we have already seen it, for example, in Franz's talk. So we start with a convex Laurent semi-continuous function. In our talk, it will be always even, in fact, that I have not written here, non-equal to plus, identically equal to plus infinity. And then the Legendre transform is a supremum on x at x scalar y minus phi of x. And as before, I want to concentrate on the case where phi is strictly convex and differentiable, so that there is an exact correspondence between the point x and the point y which reach this supremum, and you get this equality, phi of x plus L phi of grad phi of x is x scalar grad phi of x. So this is true if I assume that phi is strictly convex and differentiable. And so L phi of 0, you can compute, you replace y by 0. So this is just the supremum of minus phi of x, for example, and you can exchange. And so this is minus phi of 0. This is minus minimum of phi, but it will be phi of 0 if phi is even, and this will be our case. And so in the following, in fact, we will assume always that phi of 0 is 0. And in the case, we have L phi of 0 also 0. Okay, and what does it give as examples when you apply Legendre transform? So it was already said also in Franz talk, I think. But let's recall it very quickly that when you apply it to norm of x in a convex body square divided by 2, the Legendre transform is a norm in the polar square divided by 2. When we apply it to the convex, what's called usually convex indicatrix of k, which is 0 on k and plus infinity outside, then the Legendre transform is a norm in the polar of k. And finally, we arrive to the definition of the functional volume product, which is a product of integral exponential minus phi and integral exponential minus Legendre transform of phi. And it is again an affine invariant. It's also invariant when you add a constant to phi. And affine here means that when you compose phi with a bijective linear transform, again, it doesn't change. And it is really easy to see it after a change of variable. Okay, and as said also by Franz, Ball and Stein-Clartak-Milman proved that the maximum of the volume, functional volume product is attained for Euclidean norm to the square divided by 2 with equality, and the equality case was established by Stein-Clartak-Milman if and only if phi is a positive quadratic form. So this is for symmetric, for even functions. And it was generalized by Meyer and myself. And Le Eck also proved, gave other proof of this and other proof of our results. So he has 2 or 3 papers on this, very interesting, short proofs and everything. Okay, and now we have the conjecture. So I go to Mahler conjecture. So again, there is a conjecture in the non-symmetric case and in the symmetric case, so even and not even. But here I'm concentrating on the even case, so I haven't written even, but I should have for sure. So here is phi even. So phi even convex. The conjecture is that the volume product is minimized for L infinity norm, for example, and for L infinity norm, it will be 4 to the n. And the equality case, the conjecture of the equality case is that it is like sum. Here you have direct sum, and it's a bit like sums of, so mixtures of norm in Hanner polytope and indicatrix, convex indicatrix of Hanner polytopes. Okay. And if you apply it to this conjecture, if it would be true for convex indicatrix, this would give Mahler conjecture for sets, for convex sets. Very good. So this is stronger than Mahler conjecture for convex sets. And what is known about this conjecture? For this, not so many things are known. So it's known with Meyer, we proved it for unconditional convex functions, which proves it for in dimension 1, because in dimension 1 unconditional is just even convex function. And with Gordon, Meyer, and Reisner, we established the equality case for unconditional convex functions. And this is what, so the equality case holds. And now what I want to tell you about more recently, this is this paper with Elie Nakhle, my PhD student. And this is a submitted paper now. So if the referee is here, I can write a report. And we prove that it is true for n equals 2, so in dimension 2, and we also establish the equality case. Okay, so how do we prove it? We just adapt Meyer's approach, and we adapt here. This is a proof in dimension 1, so this is a proof we had already with Meyer. So first, let me show you this, and then I will show you how we do in dimension 2 with Elie. So in dimension 1, let's give again this proof, this adaptation of Meyer's lemma, let's say. So we start with this inequality, phi of x larger than phi of y plus x minus y, phi prime. So here there should be a scalar product, but here we are in dimension 1. So this is true for every x and y. And so what do? We multiply this by exponential minus phi of y and integrate between 0 and plus infinity. And this we call, in fact, d mu over dy. So the measure mu is exponential minus phi of y. And so what do we get? We get phi of x times integral 0 plus infinity exponential minus phi is larger than integral 0 plus infinity phi exponential minus phi plus this integral between 0 and plus infinity. And here I will write directly, I will save one line. I will write directly integration by parts. Oh no, I don't save, because I will make mistake if I save. So phi prime exponential minus phi of y dy. So here I integrate by part. I integrate phi prime exponential minus phi. So I get minus x minus y exponential minus phi of y between 0 and plus infinity. And plus, but there is, because minus 3 times, here we differentiate x minus y, so there is minus, and just what stays is integral 0 plus infinity exponential minus phi. Very good. And now this is, at plus infinity it is 0, and at 0 we get minus x, or x, times exponential minus phi of 0, but I forgot to say I take phi of 0 equals 0, because I said we can reduce to this by invariance. So let's assume phi of 0 is. So this is x. Now I divide by integral 0 plus infinity exponential minus phi, and I put on the other side. So I get x divided here, mistakes, exponential minus phi minus phi of x. So here x divided by this minus this is smaller than what do I get? This and this. So 1 here, because I divide by this, 1 minus integral 0 plus infinity phi exponential minus phi divided by integral 0 plus infinity exponential minus phi. Very good. And so this is true for every x. And again, we can see it as before. We had something true for every x. We can take the supremum on x. And when we take the supremum on x, we get L phi, because L phi of y is, so here we get L phi of 1 over this. So we get L phi of 1 over integral 0 plus infinity exponential minus phi is smaller than the same. And here this is 0 plus infinity, 0 plus infinity exponential minus phi. Okay, very good. So we get this. Now we can apply the same with L phi instead of phi as before. So we get 1 minus integral L phi exponential minus L phi divided by exponential minus L phi. I'm sorry for my bad handwriting, but okay, I hope you can see. And now we use, here I have written, because I thought I would be tired. So here I'm using x scalar y is smaller than phi of x plus L phi of y, which is our duality relation. I apply it to this quantity. This is y and this is x. So I get that 1 over p plus of phi. So here I have written below what is p plus of phi. P plus of phi, this with t equals 1, is just integral, the product of this integral 0 plus infinity exponential minus phi times integral 0 plus infinity exponential minus L phi. Okay. So 1 over p plus of phi, this is this product, is smaller than this sum. This is exactly this. And now this, we have this inequality, so we get this. So this is Mahler's ideas for functions. Very good. And now we need to recognize, because with Mahler's ideas, it was finished by induction, we had finished. But here it's not completely finished. We have to recognize what we have proved. And just, it's very short, we introduce f of t, where we change just phi by t phi. This is it. And we want to differentiate this equation. So to differentiate here, it's not so easy. So we first transform this. So the Legendre transform of t phi of y is just, by definition, supremum on x of x scalar y minus t phi of x. And we put t in factor, and this is, you get y over t here. So this is t L phi of y over t. So this is really obvious. And so we can do here, we replace by this, and we do a change of variable. So t goes out. And if we were in dimension n, t to the n would go out. Very good. So f of t is just this. Now we compute the derivative. So you can believe me, it's not difficult at all. So I did the logarithmic derivative, if you want. And it is at 1, it's f prime of 1 divided by f of 1 is 1 minus this quotient here minus this quotient. And this, you recognize exactly this, except there is 2 here, there is 1 here. So now we assume, let's assume that phi minimizes P of phi. So if phi minimizes P of phi among all convex functions, then the derivative f prime of 1 will be 0. So this will be 0. So here in this upper bound, you will get 1. And so it says that the minimum satisfy P plus of phi is larger than 1. And so every function satisfies P plus of phi larger than 1. And so P of phi, the total volume product, is larger than 4 because it is equal to 4 times the positive parts. Okay, so this is the proof of dimension 1. Very good. So the unconditional case is similar, but a bit more complicated, of course. And here I haven't told about the equality case. And in fact, for the equality case, it's a bit more complicated. So now I want to go to the n equals 2 case that we did with Elie Nakhle. So the thing is to adapt Irie-Shibata's ideas, simplified by ourselves, to the functional case. So, so mixture of this previous proof and Irie-Shibata's proof. So we introduce, for S being an hypersurface, we introduce the integral of the normal, but average with exponential minus phi of x dx on the surface. And this integral of x scalar ns of x, so this is also an oriented hypersurface to have definition for the normal. So x scalar ns of x exponential minus phi of x dx. So notice that it will, in fact, we will apply it for cones sometimes. So for a cone with apex at the origin, x scalar ns of x is always 0 when you are on the boundary of the cone. Okay, you have a cone. Maybe I should have drawn something here, 0. When you are here, the normal is orthogonal to x itself. Okay, so this will be 0. Very good. And now the lemma, the corresponding lemma for in our case is exactly this. So x, for every x again, we have x scalar something minus phi of x is smaller than something similar to what happened before, but with an extra factor q, which q is this one. Okay, why is it so? Exactly the same proof as before. You have this lower bound because phi is a convex function. You have grad phi. You multiply by exponential minus phi of y. And now, before I recall, we integrated between 0 and plus infinity. Now you integrate on any set A, let's say, with positive measure, positive phi measure. Okay. So what happens? You integrate, you multiply, you integrate, you get this. Phi of x times mu of a is larger than integral of phi d mu on A plus this integral. And now you, instead of integrating by parts, you use Stokes' formula. And this integral can be written as some integral on the boundary of A instead of A. Okay? So you apply it to some sets with boundary also. I haven't said that. Okay. I said almost. You have some normal defined on the boundary. Very good. So you get this, and this is just the result. So it's very easy. This is just Stokes' formula. Now, again, for every x, this is true. So the Legendre transform satisfies something, as before, some lower upper bound. And again, you apply it, you take A anywhere, in fact, in Rn, and B in Rn, and assume A is a cone, because this is how we will apply it. And you apply twice this, and you apply that x scalar y, again, is smaller than phi of x plus L phi of y for every x and y. You apply it for y equals this, and x equals the same thing with b and L phi instead. And you have this upper bound. So this upper bound, how you can use it? Again, as before, you want to interpret it as a differential inequality. So you introduce p plus of t as before. And as before, as I said, so p plus of t is the same as before. You apply with t phi instead of t. And here I have already done the change of variable. So there is t to the n in front, integral on r plus to the n exponential minus t phi. And here, before it was just integral between 0 and plus infinity. Here, you want to apply to grad phi of r plus to the n, which is the point which norms r plus to the n for L phi, you remember? of exponential minus TL phi. Very good. And so if you apply it to r plus to the n and you get that, you recognize that the derivative here, I'm going a bit faster, the derivative of this will give you again n minus this minus this. So here is n, and it's saying, I mean, just using this, applying, so I'm skipping a bit of thing here. Maybe I should have say, you need to work a bit. You get this, np plus of 1 plus p prime plus of 1 is larger than v plus scalar v w plus. So v plus is this with r plus to the n, w plus is this with grad phi of r plus to the n, times something. Okay, so you have this is true in dimension n. But now there is something that we cannot do in dimension n, and this is the same that we had, or that Elie Nakhle had for dimension 3. And this is the equipartition result. So the equipartition result here is easier than in dimension 3. And what we need is the following, that if you have a convex even function in R2, then there is a bijective linear map. I forgot to say, yes, I wrote bijective here, such that when you integrate on the positive part, you get 1/4 of the integral for exponential minus phi composed with t, and the same with phi exponential minus phi composed with t, 1/4 of the total. So this is just an application of the intermediate value theorem, because it's the same as saying that for our phi, there is a splitting of the space passing through 0 by 2 lines of the space of the plane, in fact, by 2 lines, so that this integral 1/4 for these 2 measures. And in fact, you see that fixing one of the line, you can rotate the other one so that one of the integral is fixed. And now you start moving the first line, and at some moment you prove that there is some oddness. I mean, the function is odd, so it vanishes at some point, and so this second integral can be equal. Very good. And what is the consequence of this? The consequence of this is that when I'm looking at p of t, which is t squared, the total integral of exponential minus t phi, now I am on R2, and the total integral of exponential minus TL phi. And p plus is the same with the positive part and the point norming the positive part, and p minus the other part. Because it's even, we only have to consider these two regions. Then, because of this equality, in fact, so here I forgot to say, I'm reducing by invariance of the volume product, I'm reducing to phi composed with t is now phi. I mean, I'm in the position where this is true with t equal identity. So here, p of 1 will be exactly 8 times this, and p prime of 1 will be exactly 8 times this derivative. And from what is here, np plus, so here n is 2. So we get 2p plus of 1 plus p prime plus is larger than this. So here, this is what I've written, but without the plus, because we just add the plus and the minus, and we get this exactly. And the q part disappears when we add 2 things. And so we get this. And now we compute what is v plus and w plus. V plus was the integral on this. So on this positive part, you can replace by integral by Stokes formula again on this. Here, w plus, you have the same, but it is on a round part which norms this part. And for Mahler functional, you can prove that this is larger than 1. And so you get larger than 32. And now, again, if you assume phi minimizes p, then you get that p prime of 1 is 0. And so you get p of 1 is larger than 16, which proves the thing. So just one word to say that for in fact, the inequality is much easier than the equality case as before. In fact, the same in dimension 3 for the usual Mahler. But we managed to follow the tracks of the equality case. And all this, as I said, was why is it so difficult, the equality case? Because we assumed strictly convex and differentiable, and you need to approximate. And when you have approximation, equality cases are more difficult. Okay, so I will stop here.